Today we're going to have a look at how we can graph the sum of two functions. Now the method is quite different depending on whether you know the equation of those functions. If you know the equation of the functions, then it's really quite straightforward just to add them together. But it's important to remember that what we're actually adding together are the y values. Why are we only adding the y values? Well, if you think about what a function is, and we've often called functions y equals f of x, which really just means that to find the y value of the function, you take some x's and do something with them. So it's a function of x. Well, if we know that a function is written in this form, y equals something, then the function, by definition, kind of is the y value. So if you're adding two functions, what you're adding is the y values of those functions. Now, easiest way to understand this is to just look at an example. Here we say if f of x is equal to this, we've got x squared plus 3x, and g of x is some other function, 2x plus 6. Graph h of x, where h of x is f of x plus g of x. Now to think about what it is that we're needing to add here, what is f of x? Well, f of x equals all of this stuff. Okay, that's what the function is. So if we're adding the function to the other function, then we can see that the formula for h of x is really just all of the f of x stuff plus the formula for g of x. And we can just simply add them together like that. Now when we tidy it up, we can get a better idea of what it looks like. We can see that it's going to be a parabola. And if we want to graph h of x, then we've got graphing techniques that we can already throw at parabolas. We've got tons of them. I can see that this one can be easily factorized. So it's going to have zeros at x equals minus 2 and minus 3. And I can see that it's an upright one. So I can easily graph this by just sketching in something like this and then reasoning that when x equals 0, y would be 6. And that's a perfectly good sketch of y equals h of x. Now I didn't actually sketch the other two. This is also a parabola and it would have zeros at x equals 0 and 3. I can tell because I can factorize it and get it looking like this. So it would be an upright parabola. This one would be a straight line, but when I added them together, this is the parabola that I've got. Now, if we don't actually know the equations of the two curves that have been added together to make h of x, and we need to somehow sketch h of x where it equals the sum of two functions, well, if we have sketches of those two functions, the basic idea is that we just need to add the y values from each function for key values of x, and then join the dots that we make with a logically shaped curve. Now that's the key idea. We're adding the y values together. So at any one point, just think, how tall is this graph here? What would be the approximate y value? And even by sort of guessing rough figures, you can come up with a pretty accurate shape. Now I say a logically shaped curve because if we're adding, say, a straight line and a parabola, then we can tell that the curve of the parabola is going to give a curve to the new compound function. And generally, you'll see that as you do more of these, it won't be too hard to kind of guess the shape that's between your key points. So this is the main idea. We're adding the y values. Now, some other considerations here that you can write down, just because these will help you sort of think things through and give you some shortcuts. If we have zeros on either curve, and remember a zero is just an x-intercept, then as we go to add the y values together, one of them's going to be 0, isn't it? So it's just going to add nothing. So that will cause our new summed function to pass exactly through the other curve at that x value, because literally we'll be adding the y value for the other curve to 0, so it's going to give us nothing extra. So looking out for zeros on either curve gives us a bit of a shortcut. If the curves meet, like actually meet each other, then it makes sense that the new curve will have double that y value for that x value. This will make sense in a moment when we do it. But basically, if we're adding two y values together and they're both the same, you could just get one and double it. Now, if the curves are ever equidistant, in other words, the same distance away from the x-axis, it'll create a 0 for our new summed curve. Well, that makes sense because if we've got two curves, let's say one is up here and one is down here, and at this point here, they're both exactly the same distance away from the x-axis, then if we add, let's say this distance was, 3, and this one was minus 3, we're going to get 0. So the summed curve is going to have an x-intercept for that value of x where it happens. The points above, in other words, all of these, should make the sign of your summed function clear. So start with easy things like zeros or points that you can easily add together, put some dots for your new summed function, join them with a logically shaped curve, and that should make it fairly clear where it sits in space. Now, if either curve is going to approach plus or minus infinity, then generally your summed curve will also do that, okay? But if one is heading towards infinity while the other heads towards negative infinity, it might actually be quite unclear what the behaviour of your new summed curve is. And that's because you might not be able to see exactly just how big each of them is in either direction to be able to tell what will happen when you add that positive number, which is really large, to that negative number, which is a really large negative, whether it's going to actually turn out positive or negative. So a little bit of careful analysis can be helpful there, but it's worth just keeping in mind that sometimes we can't exactly see. Now, before we graph a summed function where we don't know the equations, let's just have another look at our first example where we did know the equations. Now, we graphed y equals h of x in the beginning by just adding together the two functions, and then we knew how to graph it. It was a parabola that we could easily graph. But what would we have done if we hadn't had these and we just had the pictures of them in the beginning? We'll do this example first because we actually know what the answer should be. So first step, if I was graphing this one, then I might factorise the right-hand side here, and I'd get this. So then if I was reasoning that I want to let y equal 0 to find the x-intercepts, I can see that the zeros are going to be at 0 and negative 3. And that means that this is an upright parabola that has intercepts here and here. It's going to look something like this. Now, wondering how far down it goes so that we can get this point right, its axis of symmetry would be minus 1.5. So if I do minus 1.5 times 1.5, I get negative 2.25. So I need to make that go down probably a little bit lower, something like this. Okay, no, it's a bit too pointy. Let's just get it sort of roughly right. Okay, something like that. This one is a straight line. It's got a gradient of 2 and it's got a y-intercept of 6. So I know it goes through here. And a gradient of 2 is quite steep. It's a rise of 2 for every run of 1. So every 2 boxes down, it goes across 1, 2 down, across 1, 2 down, across 1. I know it goes through here too. And I could also have solved this point by saying, let's find the x-intercepts by letting y equal 0. If I let g of x equal 0, then I've got this. And so then I could say 2x equals minus 6, so x must be minus 3. Once I've got those 2 points and I know it's a straight line, I can just rule it up. Okay, so let's have a look at what we would do here to graph y equals h of x. If we weren't algebraically just adding these together, we're just working with the pictures. In other words, let's pretend that we don't even know what the equations are. We're just going off this picture. So let's look for key points. We need to add y values together. Now I can see here that they both meet here, right on the x-axis. So the y value of both of these functions here is 0. So if I add 0 to 0, I get 0. Let's put a red dot there. Over here I've got a 0 for the parabola. That means its y value is 0, and the straight line's y value is 6. So 6 plus 0 is 6. So I can put a dot there. I know that my new summed function goes through both of those points. Okay, what else can I do? Well, somewhere around here, they look like they're kind of equidistant, don't they, from the x-axis. And when they're equidistant from the x-axis, I know that my new curve is going to have a 0. Now I can see just from basic inspection here that it looks like it happens at around about minus 2. Okay, now if we were graphing this just based on a sketch and we didn't have the equation, it would be good enough to say, look, it looks like it happens around about here. Now, we know because we've already graphed this one that our new curve does in fact have a 0 at minus 2, but you can see from the graph here, even with a rough sketch like I've done, that looks about right. Okay, so we've got 3 points. What's the basic shape going to be? Well, it looks like it's going to be a parabola because one of our curves is a parabola, but then we're just adding something on. Let's put a few more dots so that we can get we can, be a bit more sure of it. Let's have a look at when x is 1. We've got a y value here of, I don't know, about 2 or 3, something like that, added to a y value of about 7. So 2 or 3 plus about 7, we're thinking something up about 10. Now, I'm saying about because these sketches aren't perfect, and I'm pretending now that we don't actually know the equations. So the y value when x is 1 of my new summed function would be way up here somewhere. So I can tell it goes up steeply. All right, what would happen in between here and here? Well, this, how tall is it here and how low is that there? Well, that looks bigger than that, doesn't it? So that tells me it's going to be still negative somewhere in here. I'm going to guess somewhere around there. All right, here we've got one of them being positive and one being negative. What gets steeper? Well, this is a straight line. It's probably heading off like that, and this one is going up more steeply. So I'm thinking that it's going to be positive. And if I start joining these things up with a sensible sort of curve, thinking of making a parabola, it makes sense that it's actually going to go up something like that. Okay, so that's the skill. I put some key points in. I judged that we were probably going to have a shape that was parabolic, and I joined them up with a line that seemed to make sense. All right, let's have another go. So here we've got a straight line, y equals f of x, and then we've got a hyperbola, y equals g of x, and we need to graph y equals h of x, where h of x is f of x plus g of x. So we're adding y values. We can start anywhere we like. How about we start here, where we've got the two graphs actually meeting? Now, what did we say about meeting points? Well, if they both have the same y value here, then the y value of our summed function will be double that. So I need to add this y value of the straight line to this y value of the hyperbola, and I'm going to get something that's twice as big, say up about here. So I can put a dot. All right, what happens over somewhere like here, out on the extremes, say? Let's just continue this one along a little bit further. Well, out here, y equals g of x is approaching 0, isn't it? So its y value is getting smaller and smaller and smaller. It's going to be virtually nothing. That means it's going to add almost no height to the other curve. So our new curve is actually going to be increasingly only just a little bit above this line, isn't it? Because if you add, say, this little height here to the height that we've got on the straight line, it's going to sit just a tiny bit above. And we can reason that as we move further to the right, our curve is going to get closer and closer to this line, y equals f of x, because we're adding tinier and tinier amounts to it. Okay, so we've got a bit of a shape here. We know we're going through this point. All right, what else is happening? Well, we've got a 0 over here on the straight line. So a y value of 0 plus the y value of negative whatever that is means that our new summed curve is actually going to sit right on the curve that doesn't have a 0 for that x value, because we've got negative something plus nothing gives you that negative whatever that is. And over here we've got another meeting point. That means for this value of x, we've got a negative number, whatever that is, doubled. So if we go down whatever that distance is, about the same again, we can put another dot. And then similar to our reasoning on this side, we can have a look here and say, look, the hyperbola has got a tinier and tinier negative y value. It's going to be virtually 0 after a while. Now, it is a negative amount, so we're always going to have a negative value plus another negative value, and that gives us a bigger negative value. We can see that our new curve is going to be heading towards this line from below, okay? Because we've always got a negative y value plus another small, but still negative y value. It's going to put it below that. All right, what's happening, say, here? We've got a y value that's bigger, the y value that's negative, and that's a bigger distance than the positive part here, isn't it? So if we add together a number, let's say this was, I don't know, 1, that would be like -3. My graph doesn't actually have any tick marks on it so that we can see numbers, but in a way that's helpful because I'm just judging proportions really, aren't I? It's kind of an art skill that I'm using here. Then I can see that our new graph is going to be negative. It's actually going to be halfway between those 2 points, somewhere around about here, and that sort of seems to line up with other dots that I've got. Now, how are we going to deal with this vertical asymptote? Well, if we're told that our new function says that we need to add the y value from each of the other functions, our hyperbola doesn't have a y value for that value of x, does it? So when we try to add it, there's nothing to add. Now, that doesn't mean it's 0. What it means is that the graph is undefined there. And if one of our graphs is undefined, it means that our new graph must also be undefined. And this kind of makes sense if you think about the behaviour of our graph as it heads towards this asymptote on the right-hand side. If you added together this y value here, whatever that is, with the y value of the hyperbola, you're getting a big number, right? And the closer you get, the more massive the y value of the hyperbola is going to be. So even though you're adding it to a fairly moderate sized y value from the straight line, it's going to go shooting up so that it's also going to approach an asymptote, just like the hyperbola does, okay? And so now we can sort of rough in some kind of shape here because we can see the behaviour of the curve in both those areas. We've got something looking sort of like this. And it makes sense that a similar thing is going to happen over on this side where we've got the hyperbola giving a really large negative number which is added to a very small positive number that's going to make virtually no difference. The new summed function is going to go into huge negative numbers here and approach this asymptote like this. So we've sort of got some symmetry here with the shape that we've got up here and the shape we've got down here. And we've actually now looked at all of the values of x. There's nothing left to do. So we've got our new sketch